Hi, what is a primitive? Primitives are important tools that we can use to compute integrals as well as to solve differential equations. In this video, we see what they are, how they are defined, what are the elementary primitives, and the first few facts about this key concept. Now, to start, we consider the operation of derivative. The derivative takes a function f and yields another function, the derivative f prime. So we may look as a map that takes functions and gives you new functions. Now, we want to do the inverse operation. So starting from an f, we want to find out who is the function capital F, if any, such that its derivative is our given little f. So what we want to do is the inverse of this operation, the antiderivative. Now, this function capital F, such that the derivative is our given little f, is just what we call the primitive of little f. A formal definition is the following. A function capital F is a primitive of little f on a certain domain D. This is very important. If the derivative of f is little f for every point of the domain D. A first remark is that if we have a primitive, we have infinitely many, because take a primitive, capital F, and just add a constant. If you add a constant, you may see that the derivative of f plus c, because of rules of calculus, this is the derivative of the sum, is the sum of the derivatives. The derivative of the constant is 0. The derivative of f is little f. So this is, again, little f. So if capital F is a primitive of little f, also capital F plus any c is a primitive of little f. Now, if we are on a domain which is an interval, this is the characterization of primitives, in the sense that if we have two any primitives of the same function little f, the difference between the two is a constant. So one is given by the other plus a constant. In other words, once you know a particular primitive, you know all the possible primitives. Now, this is easily explained, because if we take the difference between the two primitives, capital F and capital G, we call it capital H. We notice that the derivative of capital H is just the difference between the derivative of f and the derivative of g. They are both equal to little f, so the derivative of capital H is constantly 0. Geometrically, this means that the tangent to the graph of h is constantly horizontal. So this intuitively means that the function h is constant. But to be true, we need this little assumption. The domain must be an interval. In fact, if this is the case, we can show that h is constant. Pick any 2 points x, y in the interval. Now, because we are in an interval and we take 2 points x, y in that interval, everything between x and y is included in the interval. So we are allowed to apply the Lagrange finite increment formula that says that the increment hy minus h of x is equal to the derivative of h somewhere between x and y times the integral of the variable. Now, the derivative is 0, and therefore this quantity at the right-hand side is 0. This says that h of y is equal to h of x, no matter how x and y are taken in the interval I, and this means that h is constant. Be careful, because this fact depends a lot on the assumption that I is an interval. Because if the domain is no more an integral, we can have functions that have derivative constant equal to 0, but they are not constant at all. For example, here we have this function, which is minus 1 for x negative, plus 1 for x positive. It is not defined at x equals 0, so it is not correct to say that this function is not continuous at 0. It is not defined, so there is no question about continuity and differentiability, of course, at 0. But for x less than 0, the derivative is clearly equal to 0, because the function is constant, and for x positive, the derivative is as well equal to 0. And therefore, this function has derivative always equal to 0. But it is not constant. Okay? So this is an important remark. The fact that two primitives differs by a constant is true if and only if basically we are on an interval. Now let's focus on the problem of determining one particular primitive. We use the universal notation for a primitive is this one, which reminds the notation of integral because of the connection between primitives and integrals. It is also called sometimes indefinite integral, this, but I don't like too much to use the word integral for this concept because it may lead to some confusion between primitives and integrals. Integrals are numbers, primitives are functions, so they are two entirely different objects. So let's stay on the terminology of primitives. Now, for example, we know that the derivative of e to x is e to x. This relation can be seen as e to x is a primitive of e to x. So one of the primitives of e to x is just e to x. Derivative of hyperbolic sine of x is hyperbolic cosine. This says that this guy, sine x, is a primitive of hyperbolic cosine of x. And similarly, derivative of hyperbolic cosine of x is hyperbolic sine of x. So this is a primitive of this. So a primitive for hyperbolic sine is hyperbolic sine. Now imagine we want to compute the primitive for the power. So we want to find a function whose derivative is a power. We know that when we differentiate powers, we get powers. So it would be natural to look at this function as a power. Now, we have to remind that the derivative of x to beta is just beta x to beta minus 1. So if we divide by beta, assuming beta different from 0, and if we put a factor here, 1 over beta, and carry inside because of the linearity of the derivative, we have that 1 over beta, x to beta, has derivative equal to x to beta minus 1. And if we now introduce back alpha, so we call beta minus 1 alpha, this means that beta is alpha plus 1, we get this relation. The derivative of x to exponent alpha plus 1 over alpha plus 1 is just x to alpha. This at least if alpha plus 1 is non-zero, so if alpha is different from minus 1. What about the case alpha equal minus 1? In this case, we have power x to exponent minus 1. So this is 1 over x. Well, we know that there is a function whose derivative is 1 over x. It is the logarithm. At least for x positive, the derivative of log of x is 1 over x. And this says that a primitive for 1 over x is log of x. At the same time, 1 over x makes sense also for x negative. But what about log? Log is not defined for x negative. But we may observe that if x is negative, now taking the derivative of log of minus x, this is, according to rules of calculus, 1 over minus x times the derivative of the argument, which is minus 1. So minus 1 over minus x. This 2 minus goes away, and so we remain with 1 over x. So this says that the derivative of log minus x is 1 over x. Or in other words, a primitive for 1 over x is log of minus x when x is negative. We can put together these two formulas saying that a primitive for 1 over x is log absolute value of x when x is different from 0. And here we have the table for all the possible primitives for the powers. Similar, we have other primitives like derivative of sine is cosine. This means that sine is a primitive for cosine. Oh, well, the derivative of cosine is minus sine. So what if I want a primitive for sine? Well, I may notice that the derivative minus cosine is sine. So this means that a primitive for sine is minus cosine. We notice that we have determined primitives for power, and in particular, we have that the primitive for 1 over x, for when x is positive, is log of x. But what about the primitive for log? Log is an elementary function. But do you know a function whose derivative is log of x? At least we do not have this in the first table of derivatives, so it remains to be understood how to compute this primitive. Similarly, we have other funny formulas like this. The derivative of arc sine is 1 over root of 1 minus x squared. This provides a formula for the primitive of 1 over root of 1 minus x squared, which is arc sine of x. It's funny because this is not a particularly, apparently, not a particularly important function. It's just an irrational function, root of a polynomial. And we have this remarkable formula. At the same time, we do not have in mind probably what should be a function whose derivative is arc sine of x. So what is the primitive for the arc sine? Similarly, we have a formula for the derivative of the inverse of the hyperbolic sine, which is 1 over root of 1 plus x squared. And this yields this formula. So similar to the primitive that yields the arc sine. But we don't have in mind a function whose derivative is the inverse of hyperbolic sine. So we do not have, at the moment, a primitive for the hyperbolic sine. The same for the hyperbolic cosine, and the same for the tangent. Here we have a very important formula, by the way, the primitive of this particular rational function that plays a very important role in calculations. But we do not have the primitive of arctangent. So what? So we have seen the concept, the first examples. We have seen that not all the elementary functions can be computed immediately, the primitive of an elementary function. We will see in some next video this problem.